This paper is about risk-based approach to structural life assessment of oil drilling rig welded pipe. It is prepared by a couple of us from Belgrade in cooperation with Wei Li from China. In this slide, you can see risk matrix as obtained by consequence and probability categorized in both cases from 1 to 5. Since we define risk here as the product of probability and consequence, thus we have 25 different fields in risk matrix, indicating low risk in green color or medium risk, also in kind of green color, then high risk, which is red, and then very high and extreme risk. In this slide, you can see consequences described in details, taking into account effects on people, property, environment, and reputation. In combination with event frequency or probability, then we can get this green, which is low risk level, yellow, which is moderate risk level, and red, which is high risk level. Anyhow, focus here is not on a consequence, but rather on the probability. So we have introduced in a couple of previous papers how to deal with probability of static failure. And for that, we used failure assessment diagram, a simple engineering tool, and we defined probability as the ratio between a distance from the service point to the zero, this is OA, and the total distance that this service point would have if its loading was increased up to the critical value, which would be point B at the limit curve. On the other hand side, now we introduce also probability for the structural life, and once again as the ratio, in this case between the number of cycles and the total number of cycles. Total number of cycles would be the limit value that fatigue failure is expected. To explain this better, we use a case study here. It is oil rig drilling pipe, also called casing pipe. It is not that much of a problem regarding the consequence. It would be a kind of moderate consequence, something like category 3, because it affects environment and not a big deal even in that sense. But we need to estimate risk because of probability, which might be relatively high, since these welded casing pipes can contain defects of crack-like type, and they do fail from time to time. You can see typical chemical composition and basic mechanical properties in this slide. Data that we will need is for the pipe withdrawn after 70,000 hours of exploitation, which was due to maximum and minimum pressure. It was between 10 and 7.89 megapascals. Temperature was 65, number of strokes 9.6 per minute. Geometry of pipe is given in this slide. diameter is practically 140 and wall thickness 7. Now fatigue life calculation was done in two ways. Since this is simple geometry, the first way was analytical, direct integration of Paris law. The second was finite element method. It will be shown later. As for the Paris law, it's given here in the usual exponential form. Fatigue crack rate depends on two material parameters, C and M, and delta K is important parameter as well. It of course depends on amplitude loading, crack geometry given not only here but also as dependent on the ratio between crack length and the width of the component. So for the initial crack lengths which were considered here from 3.5 to 4.5, the final crack length was taken as 4.8. It was a critical crack length as estimated in some other paper. But then another two calculations were made for 1 and 2 millimeters for the purpose of comparison with the XFEM results. So if we integrate Paris law, we can get equation like this here below for the number of cycles, and for the real data, which was obtained by testing this pipe withdrawn from exploitation, we could calculate the number of cycles depending on amplitude stress and initial crack length as given in the next slide. So here we have three tables. The table number 3 shows number of cycles. Then table number 4 shows remaining life for data from the table 3. And finally, table 5 shows probabilities. You can see that for the shortest initial crack, of course, probability is the lowest, and of course it increases with the increasing of the stress amplitude. Then again, it increases also for the initial crack length, including the fact that for 4.5 millimeters, which then would grow just for 0.3 millimeters, this estimation is more than 1, but we of course say probability in that case is 1. So for 25 megapascals and 4.5 millimeters, failure is imminent. These results are also presented in this table. This is risk matrix, consequence category 3, as I mentioned, and then probability category is different. It gradually increases with increasing initial crack length and increasing stress amplitude. So the highest probability and the highest risk would be, as already emphasized, for initial length of 4.5 and stress amplitude 25. Now the same problem has been analyzed by extended FEM, and the results are shown here. We have used ANSYS to calculate crack propagation with the mesh shown on this slide. Significant difference in this calculation as to the direct integration of Paris law is that we now take into account crack axial length. It's about 200 millimeters. So crack depth is, of course, our focused crack dimension because we follow crack growth into depth. But anyhow, there is certainly an effect of crack axial length. In the case of direct integration, just to mention, the analytical way of calculating number of cycles by direct integration of Paris law, we actually look at the cross section, and crack axial length in that case would be along the whole pipe. That, of course, would produce over-conservative results, and you can see them also in this table, where we have compared XFEM with the direct integration of Paris law for different crack lengths. Then you can see that number of cycles is 2 or even more times higher with XFEM. This difference is consequence of different approach, as already explained. So we definitely need FEM if we need more precise results. But on the other hand side, if we are satisfied with over-conservative approximate results, very simple direct integration of Paris law can be quite useful and efficient. So we come to the conclusions. We have seen that simple engineering approach has been used, and it turned out to be a very efficient method to assess risk. We have applied just basic fracture mechanics concepts. More generally, it was applied for static and fatigue loading. Here presented only fatigue. The analytical tools we used, like integrating Paris law, turned out to be over-conservative, even in this simple case study. So for more sophisticated and precise analysis, we really need finite element method. And at the end, one important comment, probably the best use of this approach is to provide the gap between engineers and managers, because engineers are focused just to the problem itself. Managers typically don't understand the problem, but they know what should be the best for the company, and engineers don't know what is more general view of the company future or company economy or whatever. So they should work together. They should exchange their experience, and the best way to understand each other is to use risk matrix. Thank you for your attention.